Have you ever wondered what happens when we toss a message in a bottle into the deepest, darkest cosmic ocean? Today, we are diving into humanity's most breathtaking space expedition. Picture a pair of robotic explorers blasting off the launch pad back in 1977, originally tasked with a brief half-decade road trip to photograph Jupiter and Saturn. Fast forward almost 5 decades, and against all odds, their mechanical hearts are still beating. They have sailed billions of miles past their initial celestial pit stops. But the real plot twist happened when they finally hit the cosmic shoreline of our star system. What they found stunned the scientific world. The actual border of our solar bubble was a staggering 2.4 billion miles deeper into the dark than anyone had guessed. Our fundamental concept of this boundary's physical shape was completely backward. Magnetic forces out there twisted and tangled in utterly bizarre, unpredictable patterns. Plus, the interstellar void lying just outside broke every single rule in our physics textbooks. These pioneers sent back 7 monumental revelations, proving we were virtually clueless about our own galactic backyard. By the time this video wraps up, you will see exactly how a couple of machines powered by 1970s computer chips completely tore up the map of where our sun's territory stops and the vast interstellar ocean begins. Just a quick heads up before we blast off. If decoding the secrets of the cosmos sparks your imagination, smash that like button and subscribe to the channel. It takes just a heartbeat, yet it fuels our mission to bring these universe-spanning mysteries to fellow space enthusiasts. All right, let us set the stage. The era is 1977. The folks at NASA fling a set of twin probes into the sky, banking on a standard 5-year observational stint. Voyager 2 is the first to leave Earth, roaring out of Cape Canaveral on the 20th of August. Voyager 1 takes flight a bit later, on the 5th of September, riding a specialized express route that guarantees it will zip past Jupiter and Saturn before its twin. Their numerical titles actually hint at when they would arrive at those massive gas giants, rather than the order they left the ground. Both of these interstellar ships tip the scales at 1,820 pounds. Towering about 12 feet in the air, they are packed tight with specialized gear to analyze the 2 massive planetary kings ruling our system. Astronomers dubbed this epic voyage the Grand Tour, capitalizing on a stunning celestial traffic pattern that lines up perfectly only once every 176 years. Think of this rare planetary alignment like a series of cosmic trampolines, giving the probes a massive gravitational boost, allowing them to effortlessly slingshot across the void from world to world. This maneuver let them swing by Jupiter, Saturn, Uranus, and Neptune, all in one continuous, graceful sweep. If the solar system had not been in this exact configuration, humanity would have needed to launch 4 different rockets, burning way more chemical propellant than we could ever lift off the pad. Fortunately, the orbital dance was flawless. Mission Control jumped at the chance. Their initial blueprint was incredibly straightforward. Spend 5 Earth years scanning the massive rings and storms of Jupiter and Saturn, and then let the ships peacefully coast into the freezing dark as their batteries drain into nothingness. Not a single engineer thought these metal birds would outlive their short expiration dates. It was unimaginable that by 2026, nearly half a century later, they would still be phoning home. Above all else, nobody dreamed that their most mind-blowing revelations would bypass the giant planets entirely, stemming instead from the uncharted abyss right at the edge of the sun's influence. A border zone we wrongly assumed we had totally figured out. So, what did the brightest minds back in 1977 actually picture when they thought of the solar system's edge? They understood that our sun functions like a massive cosmic sprinkler, endlessly spraying out a torrential current of electrified particles, a phenomenon we refer to as the solar wind. Imagine an invisible gale force blowing outward in a massive bubble, racing at terrifying speeds between 250 and 500 miles every single second. This isn't normal gas. It is plasma, a violently churning cosmic stew made of free-floating protons and electrons, blazing with so much heat that atomic structures literally melt apart. We first stumbled upon the reality of this stellar breeze between the late 1950s and the dawn of the 1960s. It was brilliant University of Chicago astrophysicist Eugene Parker who initially mathematically theorized this invisible storm, years before anyone had actually measured it. Have you ever wondered what happens to the blazing edges of our star? An incredible astrophysicist discovered that the fiery crown of our sun, which serves as the absolute outer skin of its atmosphere, blazes at such extreme temperatures that gravity simply cannot lock it down. Instead, a relentless river of superheated gas constantly bursts outward into the void. When Eugene Parker first proposed this wild idea, the scientific community seriously doubted him. Experts assumed these stellar gusts were just rare hiccups, erupting only when our star threw a violent tantrum. However, satellite probes launched during the early 1960s proved that this stellar breeze actually blows without end. Through calm spells and chaotic flares alike, day in and day out, our local star sheds its own weight through the scale, blowing away roughly 1 million tons of material every single second. To us humans, that sounds like a completely mind-boggling amount of weight to lose. Yet our star is such a colossal heavyweight that it could easily keep shedding this much material for trillions of years without even making a dent. But think about it. Where does all that hurtling plasma actually end up? It cannot just keep traveling through an endless vacuum, because our galaxy is certainly not completely empty. The seemingly vacant space between stellar neighborhoods actually holds incredibly sparse wisps of gas, averaging just 0.1 atoms in a volume the size of a sugar cube. Picture it like this. The air you are breathing right now contains roughly 10 to the 19th power atoms in that exact same tiny pocket of space. That means the cosmic void is roughly 10 to the 19th power times thinner than a gentle breeze on Earth. It is a purer, more absolute nothingness than even the most advanced equipment in our laboratories could ever hope to replicate. Still, across the vast stretches of the universe, those solitary drifting particles add up to create real friction, physical pushback, and weight. And this invisible cosmic ocean is far from stationary. It is not exactly blowing toward us on its own. Rather, we are the ones plowing headfirst right through it. Picture our entire planetary family careening around the Milky Way core at a dizzying 137 miles every single second. To put that extreme velocity into everyday perspective, we are cruising at roughly 490,000 miles per hour. So, from our perspective riding right alongside our star, that sparse cosmic gas feels exactly like a fierce headwind rushing over the windshield of a speeding car. When our outbound stellar breeze finally crashes into that oncoming galactic tide, a dramatic invisible shield is born. Astronomers have named this epic border region the heliopause. Think of it as the grand gateway where our solar empire formally surrenders to the vast, untamed deep space. It is the exact battleground where the pushing force of our star perfectly matches the crushing resistance of the wider galaxy. Step past that invisible line, and you have officially left the backyard of our local star system. Out there, the raw magnetic forces of the Milky Way take over, and wild cosmic radiation races unimpeded through the dark, plunging you into a domain completely ruled by the chaotic whims of the galaxy, totally free from solar influence. During the 1980s and 1990s, researchers began feeding complex data into massive computers to visualize what this ultimate frontier might look like. They engineered incredibly detailed three-dimensional virtual simulations to study how electrified gases and magnetic fields dance together. These digital models factored in everything from swirling magnetic currents to the erratic behavior of superheated plasma, as well as the turbulent wake our star leaves behind as it slices through the cosmic deep. Based on their numbers, experts guessed this protective shield was shaped like a round balloon, perhaps stretched out slightly like a glowing comet streaking across the night sky. They pictured the backside tapering off into a long, teardrop-shaped wake trailing away from our forward trajectory. Yet overall, they believed it was a highly symmetrical, uniform protective pocket enveloping our entire planetary neighborhood at an even distance. Their math suggested this grand wall stood somewhere between 90 and 100 astronomical units away from our glowing core. For context, a single astronomical unit spans the entire gulf between our blue marble and our star, roughly 93 million miles of empty void. Therefore, this invisible cosmic fence was estimated to sit a staggering 8.4 to 9.3 billion miles away from home. Given the limited tools they possessed back then, This educated guess made perfect sense. Their virtual worlds operated on the idea that the gas between stars was perfectly smooth and evenly pressurized everywhere. They also took for granted that our home system was cruising at a relatively modest pace through the galactic sea, and they believed the outbound breeze from our star was incredibly steady and predictable. These were totally logical conclusions for the late 20th century, especially since scientists only really understood how strong this stellar gale was by measuring it right here in our own orbital backyard. Have you ever wondered where our cosmic neighborhood actually ends? By peering into the deep cosmos, astronomers were able to calculate the immense pressure of the space between stars. Crunching those numbers, they figured this invisible boundary had to sit somewhere between 90 and 100 astronomical units away. And that exact borderline was the ultimate finish line for the Voyager probes. But before bursting through that final cosmic bubble, known as the heliopause, our sun's energy crashes into a violent barrier called the termination shock. Why does this happen? Well, it's because the stream of particles shooting out from our star is traveling way faster than the speed of sound. Picture a speedboat ripping across a calm lake. The solar wind outpaces the very ripples it creates within the cosmic plasma. Just like down here on Earth, how fast sound travels out there entirely depends on what the gas is made of and how hot it is. Within that sizzling stellar exhaust, acoustic waves normally cruise at a brisk 30 to 60 miles every single second. Yet the stellar gale itself is blasting outward at a mind-bending 250 to 500 miles per second. That means our star's breath is rocketing forward at anywhere from 5 to 10 times the local speed of sound. To use the fancy science term, it's supermagnetosonic, since the tangled magnetic fields warp how these waves ripple through the void. Imagine water rushing from a faucet and hitting the sink basin. When that hyper-fast flow hits the resistance of deep space, a massive shock wave piles up right in front. We experience the exact same physics when a fighter jet breaks the sound barrier and unleashes a deafening sonic boom. And beautifully enough, those same laws of physics govern the superheated plasma in the vacuum of space. Hitting that termination shock is like slamming on the cosmic brakes, violently forcing the stellar winds to drop below the speed of sound. The speed plunges drastically, dropping from a blistering 250 to 500 miles per second, down to a sluggish 50 to 100. As a result, the particles get squished together and superheated, packing 3 to 4 times more matter into the exact same amount of space. Meanwhile, the sheer friction of this cosmic pileup sends the temperature skyrocketing even higher. This violent boundary acts like a gigantic slingshot, accelerating stray particles to unbelievable speeds. Powerful magnetic forces trap and whip these particles into a frenzy, with early math suggesting this turbulent zone sat around 75 to 90 astronomical units away. That placed this chaotic speed bump significantly closer to home than the actual edge of our solar bubble. But this boundary breathes like a living thing, shifting closer or farther depending on the sun's temper. When our star acts up during its peak activity, it exhales a much fiercer, denser gust of stellar wind. That extra muscle pushes against the interstellar void, forcing the shock wave much deeper into the darkness. Conversely, when the sun goes quiet and its breath weakens, the crush of deep space pushes that boundary right back toward the planets. Now, nestled right between that initial crash zone and the absolute edge is a thick layer we call the heliosheath. Picture a river hitting a boulder. The sluggish, boiling plasma has to divert, washing sideways as it struggles against the immense pressure of the greater galaxy. Far from a gentle stream, navigating this outer shell is a completely chaotic ride. It's a furiously churning, swirling whirlpool of stellar matter. The area is plagued by twisting magnetic knots and violently unstable pockets of electrified gas. Yet despite the total chaos, almost every single particle thrashing around out there was still born from our very own sun. Scientists guessed this messy transitional bubble stretched out for a massive 10 to 20 astronomical units. It serves as the ultimate cosmic waiting room, bridging the gap between our sun's exhausted influence and the cold, uncharted ocean between stars. Once you finally pierce the heliopause, a terrifying new force takes over. Galactic cosmic rays. These are atomic shrapnel shot out by detonating stars and the most cataclysmic explosions happening across the Milky Way. Luckily for us on Earth, Our sun's constant outward breeze and magnetic wrapping paper deflect the vast majority of this deadly radiation. A few stray bullets do manage to pierce our bubble, but their destructive power is heavily watered down by the time they reach us. In a very real way, our solar system brings its own giant invisible force field. It bats away or severely cripples those incoming stellar bullets long before they can threaten the rocky worlds close to the sun. Step outside that protective shell, though, and the sheer volume of that radiation spikes drastically. Researchers calculated that anyone braving that deep void would face 2 to 3 times the radioactive bombardment we measure near our home planet. And you wouldn't get a gentle warning either. Crossing this ultimate boundary is like stepping through a solid door. Our best math predicted a spacecraft would punch through that final shell and plunge into true interstellar space in merely a few weeks or months. In an instant, the familiar wave of solar material bathing the probes would simply vanish. Or at the very least, it would fade away into a barely detectable whisper against the vast silence of the universe. Have you ever wondered what happens at the very edge of our solar system? Scientists initially figured that high-energy radiation pouring in from deep space would suddenly spike. They expected our probe's internal compass to instantly flip as it traded our sun's protective magnetic bubble for the wider galaxy's invisible forces. After all, the interstellar magnetic web was supposed to point in a completely different direction than our local solar weather. Think of our star's magnetic influence, like the spokes on a bicycle wheel, pushing straight out into the dark void, even if those invisible lines get warped and braided as our star constantly spins. Meanwhile, the greater cosmic field is shaped by the grand sweeping spiral arms of the Milky Way itself. Researchers calculated that these two massive cosmic currents would clash at a very sharp, dramatic angle. So when crossing that ultimate border, the heliopause, our robotic Scout's sensors were supposed to go absolutely crazy with new readings. Solar particles dropping to zero, deep space radiation shooting off the charts, and the magnetic alignment shifting completely. All of this unfolding quickly over just a few weeks or months. Astrophysicists felt incredibly sure about this storyline because the math governing magnetic fluids was considered rock solid. We had spent dozens of years analyzing how cosmic shock waves and charged gases behave in a vacuum. Countless hours had gone into polishing and perfecting these theoretical blueprints. Sure, the exact mileage might be slightly off, but the grand architecture of the border was assumed to be a guaranteed match. Picture a massive collision zone somewhere between 75 and 90 times the distance from Earth to the Sun. Following that, a turbulent outer crust stretching 10 to 20 astronomical units deep. Finally, a crisp, well-defined wall roughly 90 to 100 units out, clearly splitting our solar neighborhood from the vast interstellar void. But guess what? Reality threw them a massive curveball, completely shattering those carefully crafted theories. And that shocking plot twist was merely the opening act of an incredible cosmic mystery. To truly grasp the magic of these revelations, we have to look closely at the ancient hardware that actually pulled it off. Because the sheer miracle of the Voyager mission relies on electronics dreamed up and bolted together way back in the early 1970s. Picture an era long before glowing smartphones, the World Wide Web, or even desktop computers existed. The electronic brains flying inside these probes are almost hilariously basic compared to the tech we use today. Every probe relies on a trio of dedicated processing units acting as a team. One module's entire job is catching the driving directions we beam up from ground control. A second brain strictly handles crunching the raw scientific numbers gathered from the stars. Meanwhile, the third piece acts like an inner ear, keeping the antenna perfectly aimed back toward home. Combine all three, and you get a grand total of roughly 68 kilobytes of digital storage. That device resting in your pocket right now holds millions of times more space than both twin spacecraft put together. Yet somehow our brilliant programmers are still beaming up entirely new software fixes to these antique machines. Back in 2002, the space agency successfully bypassed a dying chip on Voyager 1 by sending it a fresh set of digital instructions. Then in 2013, they commanded the second probe to ignite reserve engines that had been sitting frozen for 37 straight years. Amazingly, those dormant rockets roared to life without a single hiccup. Try wrapping your mind around fixing 50-year-old code on a machine flying billions of miles out of your physical reach, knowing that every single keystroke you send requires more than 22 excruciating hours just to cross the dark void. Their beating heart is a specialized atomic battery known as a radioisotope thermoelectric generator, or RTG. Each ship carries 3 of these devices, loaded up with glowing spheres of plutonium-238. As that radioactive material slowly breaks down over time, it naturally gives off intense warmth. Special sensors inside the batteries catch that thermal energy and spin it into usable electric juice. When they first left the launch pad, these nuclear engines pumped out roughly 470 watts of power. However, nuclear fuel inevitably cools off, bleeding roughly 4 watts of precious energy every single year. Fast forward to 2026, and Voyager 1 is limping along on just about 249 watts remaining. This slowly fading heartbeat is the ultimate threat to the mission's survival. Every single camera, warming unit, and radio dish has to fight for a sip of that rapidly vanishing power supply. Have you ever wondered what it feels like to slowly fade away in the freezing dark of space? As the nuclear heartbeat of these explorers begins to fail, Mission Control faces an agonizing choice. Which robotic senses must be permanently blinded to save power? The visual journey actually ended decades ago. Back in 1990, we permanently closed their eyes to save juice. And ever since, we've been systematically unplugging their remaining instruments, one by one. Sometime in the twilight of the late 2020s, the very last drops of energy will bleed out, leaving these historic pioneers completely paralyzed. They will transform into silent ghost ships drifting through the cosmic ocean. But for now, they still whisper to us, tethered to home by an invisible lifeline known as the Deep Space Network. Picture 3 gigantic metallic ears strategically planted across the globe, one in California, one in Spain, and another in Australia. This genius global setup ensures that as our blue marble spins, we never, ever lose our line of sight with these lonely wanderers. Imagine a communication dish the size of a football field, stretching a staggering 230 feet across, staring wide-eyed into the starry void. Distance completely bends our reality here. A simple radio ping from Voyager 1 trudges across the vacuum for more than 22 agonizing hours before hitting our antennas, while Voyager 2's messages lag by roughly 18 hours. Imagine giving driving instructions to a remote-controlled car, only you have to sit and wait an entire day just to see if it even heard you. And then, you wait another full day just to get a digital thumbs up back. A single basic conversation with Voyager 1 consumes a staggeringly long 44 hours of nail-biting silence. Now, how loud are these interstellar shouts? Barely a whisper. They broadcast at roughly 23 watts, which is actually weaker than that cheap LED bulb lighting up your closet. After fighting its way across billions of miles of empty, unforgiving space, that tiny beacon of light degrades into a nearly imperceptible ghost of a signal. We are talking about 1/quintillionth of a watt, a fraction of a spark, making it the absolute faintest trace of data humanity has ever managed to catch and translate. Yet somehow this ancient, fading whisper is exactly what shattered our entire understanding of the solar system's absolute edge. We are mapping the absolute unknown, using electronic brains that have less processing memory than the microwave sitting in your kitchen. Their voices are dimmer than a refrigerator light, and their intricate hearts were engineered on paper with slide rules decades before the modern internet was even born. Hold on to that thought, because armed with this primitive, archaic hardware, what these twin pioneers discovered out there left the world's most brilliant astrophysicists utterly speechless. Let's journey out to the termination shock, the chaotic, violent border wall of our sun's territory. On December 16, 2004, history was quietly made in the pitch-black void. Voyager 1 was drifting an unfathomable 94 astronomical units away from our star. That is a dizzying 8.7 billion miles out into the deep. Now, the smartest minds on Earth had bet good money that this cosmic boundary would pop up somewhere between 75 and 90 AU. But our fearless probe kept cruising, blowing right past those predictions like a car missing a highway exit. Think of a raging river crashing into an ocean. The termination shock is exactly that. The violent collision zone where a hurricane of supersonic solar wind suddenly slams into a wall, and plummets to subsonic speeds. It isn't just an imaginary line on a map. It's a brutal, chaotic barrier of highly compressed, scorching hot plasma roaring against the interstellar tide. And to everyone's absolute bewilderment, our little spacecraft stumbled into this tempest much deeper into the dark than anyone anticipated. But here is where the story takes a weird turn. Stepping out of our solar system wasn't a clean, simple crossing. Back on August 1st, 2002, at 85 AU, Voyager felt the first turbulent ripples of the edge. But then, the edge seemingly ran away. Over the next few months, this massive cosmic wall literally pushed itself further out into the galaxy. Suddenly, our probe was floating back inside the sun's safe harbor, riding the fast solar winds again, as if the boundary had simply vanished into thin air. Fast forward to 2003, and bam! The invisible wall slams into Voyager a second time. It was like standing on a cosmic beach. The shockwave washed over the metallic explorer like a high tide, only to rapidly recede back into the interstellar ocean. It wasn't until that fateful day of December 16, 2004, that Voyager truly broke through the surf, once and for all, leaving the fast winds behind to sail permanently into the thick, sluggish plasma of the great unknown. Why did the boundary act like a phantom? Because incredibly, our solar system literally breathes. Think of the sun like a giant set of lungs. When it exhales violently during massive solar storms, the sheer force of that blast expands our protective bubble, pushing the border wall outward. When the star calms down and takes a breath in, the bubble deflates and the border shrinks back. It isn't a rigid glass shell. It's a dynamic, living organism. Then comes Voyager 2's turn to shine. On August 30th, 2007, it finally pierces the veil, but it hit the boundary at just 84 AU, roughly 7.8 billion miles away from home. Hang on a second. Did you catch that? Voyager 2 breached the wall, significantly closer to our star than its twin did. We are talking a massive discrepancy here, about 10 astronomical units, or an astonishing 930 million miles closer. If our solar system's shield was a perfect, neat little sphere like we always drew in grade school, both ships would have hit the edge at the exact same distance. This was a monumental mic drop moment for astronomy. It provided the absolute first proof that our sun's protective bubble is far from perfectly round. Instead, it's warped and battered, squashed inward on some sides and stretched way out on others, reacting to the extreme pressures of deep space. It turns out, Voyager 1 has been surfing right toward the nose of this warped shield, the exact leading edge where our entire solar system plows headfirst into the Milky Way galaxy. Have you ever wondered what happens when humanity sails off the absolute edge of our cosmic map? While its twin forged straight ahead, Voyager 2 actually veered off to aggressively carve a path toward the lateral flank of our solar system. Picture a ship plunging through violent ocean swells. Similarly, the leading edge of our solar bubble gets tightly squeezed together by the forward momentum of our home star. Meanwhile, its sides and wake get violently dragged out into a massive, uneven teardrop, allowing these two robotic pioneers to taste completely distinct zones of this lopsided cosmic shield. For decades, brilliant astronomers harbored a strong hunch that our solar boundary was wildly misshapen. Today, they finally possess the cold, hard data to definitively back it up. Bursting through the chaotic boundary line known as the termination shock, both spacecraft boldly plunged right into a bizarre, uncharted frontier dubbed the heliosheath. On paper, this leg of the journey was expected to be relatively boring, merely a place where sluggish streams of stellar plasma wash outward and scatter harmlessly to the sides. Think of it as a choppy yet entirely predictable waiting room, a vast, simmering buffer zone safely separating our protective solar bubble from the deep, dark void of interstellar space. Researchers safely assumed it would take these intrepid mechanical explorers anywhere from 5 to 10 long years to finally navigate across this cosmic waiting room. They had to endure this massive stretch before ultimately hitting the grand finish line, the heliopause. Theoretical models suggested this chaotic buffer layer spanned a staggering 10 to 20 astronomical units in sheer thickness. Crunching the numbers on the trajectory and velocity of Voyager 1, Experts enthusiastically circled the year 2015 on their calendars, predicting the grand breakthrough at roughly 100 to 110 astronomical units out. However, as the calendar flipped to 2010, the cosmos threw an unimaginable curveball at the team back on Earth. Suddenly, the first spacecraft's delicate sensors started getting bombarded by a wildly escalating barrage of highly energetic galactic cosmic rays. We are talking about blistering subatomic shrapnel blasted outward by dying stars, colossal supernovae, and the most brutal cataclysms in the known universe. Textbooks practically dictated that the sheer volume of this stellar radiation should only spike dramatically once the probe slammed into the actual heliopause, deep inside the heliosheath. Curiously enough, the gentler, localized breeze of particles blowing off our own sun began to simultaneously drop entirely off the radar. Again, the established science insisted that this familiar solar radiation would only hit absolute zero at the final borderline. There was absolutely no logical reason for them to slowly bleed out and vanish prematurely. Yet, by all orbital calculations, the mechanical traveler was undeniably still wading directly through the thickest part of the heliosheath. Its onboard gear was still tasting the solar plasma, and the surrounding invisible magnetic lines still undeniably carried the distinct, swirling signature of our home star. So, what kind of dark cosmic magic was at play here? By June of 2012, the distant pioneers stumbled upon a breathtaking phenomenon never witnessed by human eyes before. It smoothly sailed straight into a mysterious pocket of space, where the magnetic currents suddenly snapped into perfectly straight, outward-facing alignments. Instead of a chaotic, tangled mess of cosmic spaghetti, these fields were impeccably ordered, aiming out into the deep dark like precisely drawn arrows. Astonishingly, subatomic material was vigorously surfing along these invisible tracks in a high-speed, dual flow. Material from our sun was sprinting outward toward the void, while violent galactic radiation came aggressively racing right back down the exact same lanes. These perfectly straightened currents were functioning identically to a massive cosmic freeway, establishing a clean, direct link between our solar buffer and the great galactic beyond. Awestruck astrophysicists quickly dubbed this bizarre, breathtaking interstellar interchange the magnetic highway. Not a single mathematical simulation had foreseen this anomaly. Quite frankly, the scientific community never even dreamed such an architectural marvel could naturally exist out there. The reigning hypothesis passionately suggests that our sun's invisible influence is literally reaching out and cleanly splicing itself together with the broader magnetic web of the Milky Way. Because of this seamless connection, high-speed matter can effortlessly commute back and forth across the cosmic border. Imagine a beautifully engineered superhighway, effortlessly linking two entirely isolated, profoundly alien territories together. For roughly 2 agonizingly tense months, Voyager 1 cruised straight down the center of this surreal interstellar transit tube. Throughout that specific stretch, the relentless bombardment of galactic radiation spiked to terrifying levels entirely unseen anywhere else inside the buffer zone. Conversely, the familiar wash of comforting material from our sun dropped down to an absolute trickle. The plucky robot was effectively taking a thrilling sneak peek at the grand open cosmos, tapping right into the deep void despite technically remaining safely inside our solar borders. Then, on the fateful day of August 25th, 2012, the established scientific rulebook got completely thrown out the window. The comforting breeze of our star virtually evaporated into sheer nothingness, while violent deep space radiation instantly maxed out at a terrifying constant hum. This violent atmospheric shift took mere days to finalize, yet weirdly enough, the overarching magnetic compass needle utterly refused to budge. It stubbornly maintained the exact same unwavering orientation it had confidently held throughout its entire epic journey across the solar buffer zone. Naturally, this bizarre paradox threw the brightest minds back on Earth into an absolute tailspin of profound bewilderment. Half the room passionately claimed that our mechanical ambassador had finally punched completely through the ultimate boundary into the great unknown. After all, the total blackout of familiar stellar plasma and the massive, undeniable surge in foreign radiation served as incredibly solid evidence for a true galactic exit. Conversely, Vocal skeptics argue that the stagnant magnetic alignment proved the probe was still solidly trapped, suggesting it had merely wandered into a weird, uncharted cosmic purgatory. It leaves us deeply wondering as we stare up at the night sky. Could the ultimate edge of our solar system actually be built like a massive cosmic onion, hiding countless mind-bending layers just waiting for humanity to peel them back? Have you ever wondered exactly where our cosmic neighborhood ends? For well over 12 months, the brightest minds in astronomy fiercely argued that exact question. Ultimately, by the fall of 2013, space agency officials made a historic declaration. Our intrepid robotic explorer actually pierced the solar bubble back in 2012. That legendary probe drifted a staggering 121 astronomical units away, a mind-boggling distance of 11.2 billion miles from our blazing star. To put that into perspective, early computer simulations completely missed the mark. Instead of hitting the cosmic border at a predicted 90 to 100 astronomical units, our probe sailed all the way past the 120 mark before breaking through. We are talking about a boundary pushed outward by a massive 20 to 30% margin. Imagine missing your target by a whopping 2.4 billion miles. That enormous miscalculation became the first jaw-dropping revelation of this journey. Essentially, the grand shield protecting our planetary family was hiding much deeper in the dark void than anyone guessed. This wasn't some tiny rounding glitch. Astrophysicists were off by billions of miles. Such a massive gap left us with a puzzle. Either our star's outbound gusts were far mightier than we knew, or the deep space gas outside was surprisingly flimsy. Perhaps even a mix of both. Digging into the data later revealed the truth. The cosmic ocean we are swimming through is quite a bit thinner than researchers previously believed. While it isn't completely empty, that slight drop in pressure was all it took to stretch our protective bubble outward by up to a third. Why should we care about this invisible wall? Because that magnetic balloon acts like a giant deflector shield, keeping brutal high-energy radiation from deep space away from our delicate home. A wider, puffier barrier translates directly to vastly superior protection for everything inside. Over millions of years, the strength of this cosmic umbrella determines how much stellar radiation bathes our world, potentially altering our climate, shifting the chemical makeup of our sky, and even steering the course of genetic evolution. Yet, the sheer size of our stellar neighborhood was merely the opening act of this scientific drama. For decades, textbooks painted our solar domain as a perfectly round, symmetrical globe. At best, theorists guessed it might stretch out just a tiny bit in the wake of our star's travel path. Picture a glowing comet streaking through the dark, keeping a neat and balanced shape. But the actual structure turned out to be wildly different. Instead of a neat sphere, our protective shell resembles a speeding bullet or a warped teardrop plunging through the abyss. At the leading edge, where our star rams into the galactic wind, the bubble gets smashed flat into a thick, stubby nose. Meanwhile, the flanks are squeezed tight, and an incredibly long tail trails behind us, likely dragging on for hundreds of astronomical units. Remember how our first probe broke through at 121 units? It was driving straight into that blunt front end. Then came its twin, making its own grand exit on the 5th of November, 2018, punching through at around 119 astronomical units away. However, this second adventurer took a totally unique trajectory, angling much closer to the sidewalls of our bubble. Surprisingly, both crafts hit the boundary line at almost the exact same mileage from our blazing center. That fascinating clue proved the middle of our bubble isn't stretched out like a cigar. The oddities in its shape are actually quite delicate. So what crushes the front of our shield? It is all driven by our star's relentless plunge through the Milky Way. Our blazing host is hurtling through the local galactic neighborhood at a blistering pace of 137 miles every single second. To frame that for you, we are cruising at roughly 490,000 miles per hour through the cosmic void. If you were riding shotgun on the sun, the surrounding space gas would feel like a furious hurricane blasting directly into your windshield. That massive friction is exactly what squashes the leading edge of our solar bubble. Just past that crumpled front door, physics tells us there should be a massive ripple of energy echoing through deep space. Think of the cresting wave rolling ahead of a speedboat. Theorists guess this invisible galactic surf breaks somewhere between 140 and 230 astronomical units away. However, considering how spectacularly those early guesses failed regarding the main border, that crashing wave could honestly be lurking anywhere. As of right now, our legendary twin probes are still sailing through the dark, waiting to hit that turbulent swell. Why get so obsessed with the exact geometry of this bubble? Because its contours dictate exactly how deep space radiation sneaks into our planetary backyard. If we actually lived inside a perfect sphere, those dangerous radioactive particles would bombard us evenly from every possible angle. But living in a bullet-shaped shield means those cosmic intruders find weak spots, slipping through far easier on certain sides. In fact, that long trailing wake behind our star could act like a sneaky back door, letting radiation funnel straight toward us from the rear. Beyond just radiation, this bizarre geometry totally changes how our little neighborhood collides with the giant clouds of gas drifting between the stars. Right now, our entire planetary family is plunging through a cosmic fog bank known as the local interstellar cloud. Think of it as a thicker, more congested pocket of dust and gas floating in the galactic ocean. This massive celestial cloud bank spans an incredible distance of several light years from edge to edge. As we scrape against the borders of this colossal fog, the shifting pressures constantly mold and squeeze our protective bubble, reminding us that we are just Voyagers sailing through a much wilder, profoundly mysterious universe. What happens when our solar system finally sails into uncharted cosmic waters? Fast forward a few millennia, and our sun will inevitably drift out of its current stellar neighborhood and plunge into a completely different galactic zone. When that epic crossing happens, the surrounding cosmic pressure will shift dramatically, causing our heliosphere, that massive, invisible shield protecting our planets, to warp and completely morph in scale. Right now, our intrepid Voyager probes are simply capturing a fleeting photograph of this magnificent celestial shoreline exactly as it stands today. Any futuristic spacecraft we launch generations from now could encounter a completely unrecognizable barrier out there in the dark. That brings us to a truly mind-bending revelation. Our textbooks had the shape of our solar system completely wrong. Instead of a perfectly round, static balloon, imagine a lopsided, constantly shifting teardrop, battered and sculpted by our sun's relentless plow through the Milky Way. Astrophysicists originally assumed that bursting through this final frontier into deep space would be a neat, sudden event. They pictured a crisp dividing line where the warm solar winds would simply vanish within a matter of weeks. They expected deep space radiation to suddenly spike, while the magnetic compass would violently snap into a new direction. Just a simple, undeniable stepping stone into the great cosmic void. Reality, however, was far messier, as Voyager 1's agonizing way through this turbulent outer edge took well over 2 years. Back in 2010, deadly galactic radiation began creeping upward, yet the craft remained completely bathed in our sun's familiar warm plasma. Then in 2012, the probe stumbled into something utterly bizarre. A sprawling magnetic superhighway. Think of this as a cosmic interchange, a strange transition zone where high-speed particles race freely along invisible tracks, linking our solar neighborhood directly to the interstellar abyss. Finally, on August 25, 2012, the steady breeze of solar material flatlined entirely. Galactic radiation surged violently, but strangely, the magnetic compass never flipped, plunging the scientific community into months of heated arguments. The puzzle pieces eventually clicked. Out there in the dark, the galaxy's magnetic alignment just so happened to perfectly mirror our sun's own magnetic orientation. It was an absolute astronomical fluke. Slipping through that barrier triggered no wild compass swings, simply because the invisible magnetic currents on both sides were flowing in the exact same direction. But the cosmic narrative shifts wildly when we look at Voyager 2's grand exit. Unlike its twin's prolonged crawl, this probe pierced the veil in a mere 24 hours on November 5, 2018. A blistering fast getaway. And this time around, the instruments registered an unmistakable pivot in the magnetic forces. It shifted by roughly 20 degrees, nothing chaotic but undeniably there, which begs the question, why such drastically contrasting experiences? Because these two mechanical pioneers shattered the boundary at completely different coordinates. Our solar system's armor is far from perfectly smooth or uniform. Up at the leading front, where Voyager 1 broke through, the so-called nose of our star system, the protective shield is violently smashed inward. That intense pressure likely creates a dense, complex outer shell, making those strange magnetic transit lanes a localized feature of that specific region. Meanwhile, sliding out through the flank where Voyager 2 escaped, the dividing wall is incredibly crisp, allowing for a much sharper transition. The invisible magnetic architecture out on the side edges simply behaves by a totally different set of rules. Yet, both trailblazers reported something deeply unsettling even after they supposedly left. The boundary was vibrating. Picture this. Nearly 12 months after waving goodbye, Voyager 1 was suddenly splashed by solar matter again in August 2013. And just as quickly as the cosmic tide rushed in, it pulled back into the void. The edge of our home system had literally surged forward to swallow the probe again before retreating, a phenomenon entirely driven by the temperamental outbursts of our sun. Massive tsunamis of stellar energy constantly radiate outward from the heart of our system. Upon slamming into the ultimate outer wall, these colossal waves violently shove the heliopause deeper into interstellar space. This invisible skin stretches far beyond our speeding spacecraft, only to snap back like a cosmic rubber band once the storm's fury dies down. The Voyagers essentially felt the heartbeat of our solar system, a gargantuan entity rhythmically expanding and shrinking to the tune of violent stellar eruptions billions of miles in the rearview mirror. The sheer distance is so vast that the ripple effect from a solar tantrum in 2012 might take ages to hit the shoreline. It might not actually crash into that final frontier until 2014 or even 2015. Nobody saw this incredible dynamic behavior coming. Early computer simulations painted our cosmic border as a rigid, sluggish wall that only barely shifted over decade-long solar cycles. They certainly never expected it to violently flutter back and forth within a matter of mere weeks. Nor did they anticipate a barrier so restless that it could repeatedly wash over a motionless observer, plunging them in and out of the solar system without them taking a single step. Ultimately, this reveals a profoundly humbling truth. The absolute edge of our celestial neighborhood is a living, breathing phantom. You cannot simply draw a clean chalk line on a star map and declare, "This is where home stops." This living wall surges back and forth by billions of miles in the blink of a cosmic eye, begging the ultimate question. If you park your ship exactly 120 astronomical units out, have you truly left the solar system? The reality is, the answer changes by the day. Right at this very second, you might be drifting in the deep interstellar ocean, just waiting for the tide to pull you back in. Which we are talking about bouncing back and forth across the border, surfing along magnetic superhighways, and riding bizarre energy ripples. So much for the very first time in human history, our brave little probe, Voyager 1, was actually tasting the raw material of the galaxy. Up until this historic milestone, everything we knew about the dark gaps between stars was essentially gathered by peering through telescopes from afar. We relied entirely on decoding the light signatures from faraway suns and listening to the faint radio hums echoing off giant gas clouds. Throw in a hefty dose of mathematical guesswork and chalkboard physics to tie it all together. But our robotic scout changed the game by actually reaching out, physically touching the cosmic void, and beaming back the hard numbers. What did it find out there? A staggeringly empty environment, hovering right around 0.08 specks of matter for every tiny cubic centimeter. To put that into perspective, humanity's absolute most advanced laboratory vacuum chambers still leave behind roughly 1 million stray particles in that exact same space. That means the deep cosmos is vastly emptier and more pristine than any artificial void we could ever hope to manufacture down here on our home world. Yet here is the truly wild part of the story. It is not entirely devoid of stuff. If you scale that up to a volume the size of a large cardboard box, you still end up with about 80,000 microscopic bits floating around inside. Now compare that to taking a deep breath down at the beach, where that exact same box would be packed with an unimaginable 10 to the 25th power molecules of air. The great galactic ocean is effectively 10 trillion times thinner than the very atmosphere keeping you and me alive right now. Still, there is undeniably a physical presence lurking in the dark, and that sparse material is shockingly energetic, clocking in anywhere from 54,000 to 90,000 degrees Fahrenheit. Now, before you imagine a blazing inferno, remember that in physics, this just means the few scattered atoms are vibrating insanely fast, rather than creating a massive, warming fire. Because it is basically a ghost town out there, those blazing fast atoms simply cannot bump into enough things to actually transfer warmth. If you somehow floated out there without a spacesuit, you would not incinerate. You would instantly turn into a block of solid ice, simply because the emptiness cannot pass its energy onto your skin. As for the physical weight of this cosmic sea, it pushes at an incredibly fragile 0.000000003 pascals. Down here on the ground, our sky constantly presses against our shoulders with a relatively crushing 101,000 pascals. That makes the outward push of the deep galactic void roughly a minuscule 1/10 trillionth the strength of our everyday environment. Yet, incredibly, this phantom whisper of a force is exactly what eventually brings our mighty sun's solar hurricane to a dead halt at the cosmic shoreline. As ghostly and fragile as it is, the sheer endless volume of it provides enough resistance to completely dam up the outward rush of our entire star system. As our probe sails deeper into the unknown, its sensors begin picking up a bizarre humming effect. Literal vibrations rippling through the charged cosmic gas. Think of it like invisible sound, sweeping waves that squeeze and stretch the scattered matter as they roll across the eternal dark. Way back in 2012 and 2013, the brave craft actually recorded a handful of these powerful shock waves ringing out like a bell. By carefully tuning into the pitch of those cosmic songs, researchers back home figured out exactly how tightly packed the loose electrons really were. The plot thickens though, because every time they checked the math, the numbers kept shifting around. It turns out that the galaxy's breath is far from a smooth, even mist. It is surprisingly clumpy and textured. The thickness of this invisible fog jumps up and down by 10 to 20%, just by moving a few astronomical units in any given direction. These thick patches